AP Chemistry, this is Lesson 8, Covalent Bonds. So, covalent bonds occur when two or more atoms share electrons. Covalent bonds occur primarily between non-metals such as carbon, nitrogen, oxygen, phosphorus, hydrogen, sulfur, and chlorine. Covalent bonds produce combinations of atoms called molecules. And covalent bonds are the bonds that are found in you and other living organisms. So remember, covalent bonds they share electrons, valence electrons. So when nonmetals bond, they pull on each other's electrons very hard because they both have high electronegativities. Upper right-hand corner of the periodic table has the highest electronegativities. Since they both have high ionization energies, they don't easily give up electrons. It is two strong guys having a tug of war. Nobody wins. So consequently, the two atoms share electrons. So let's compare that to ionic bonds. Ionic bonds are between nonmetals on the right, where you see those two guys, and the metals over on the left, which are weak guys. They have low ionization energies. They easily give up electrons. So nonmetals, the strong guys, take electrons away from the weak guys, the metals. That makes the nonmetal negatively charged, an anion, and the metals become positively charged, a cation. The positive and the negative attract each other. Here you have a situation where the two atoms are both strong guys. They're both nonmetals. Neither one is strong enough to take the electron away from the other. Therefore, they end up sharing electrons. That's what the word covalent means. Co means together, as it like in the word cooperate. And valent means valence electrons. So they share or they work together. Their valence electrons are shared or they work together. The octet rule says that atoms are most energetically stable. We can just use the metaphor happy when they can fill their valence orbital, their outer orbital. Octet means 8. It's called octet because elements in the second period rows and below need 8 electrons to fill their valence outer orbital. So this is an oxygen atom that you're looking at right here. So oxygen has 6 electrons in its valence orbital. To be happy, oxygen would like to fill the 2 empty spaces in the valence orbital. But how does it do this? Where does it get those electrons? The octet rule says that atoms are most energetically stable. That's the phrase you would want to use on the AP exam, energetically stable, not happy. Don't use metaphorical words like that. Is most energetically stable when they can fill their valence orbital. Octet means 8. It's called octet because elements in the second period and below need 8 electrons to fill their valence orbital. Hydrogen's valence orbital can hold only 2 electrons. So hydrogen needs 1 electron to be happy and fill its valence orbital. But how? And note, even though hydrogen's first orbital can only hold 2, not 8 electrons, it's still called the octet rule. The main idea is that an atom wants to fill its valence orbital to be happy. So here's how they can work to form a covalent bond. Each hydrogen shares its electron with oxygen. This gives oxygen a total of 8 valence electrons, so oxygen's happy. So we'll see them coming together here. Oxygen shares an electron to fill the valence orbital of each hydrogen, so the hydrogens are happy. So we see the first hydrogen and oxygen pair up, and they share electrons. Oxygen shares that electron with hydrogen, and hydrogen shares its electron with oxygen. On the right, you see that the same thing will happen. So they come over, oxygen shares that electron with hydrogen, hydrogen shares its electron with oxygen. So those are the shared electrons. Because two hydrogens fill the valence orbital of oxygen and oxygen fills the valence orbital of two hydrogens, this combination creates water, H2O. Notice that those electrons that are shared in the purple there, they're being double counted. They're being counted as 2 electrons for hydrogen, but they're also being counted as 2 valence electrons for oxygen. And on the right, it's the same thing. Those 2 on the right count as 2 valence electrons for hydrogen, but those same 2 electrons count as 2 valence electrons for oxygen. So you're effectively double counting those electrons. These electrons are double counted. They both belong to the hydrogen atom, and at the same time they both belong to the oxygen atom. Similarly, these electrons are double counted. They both belong to the hydrogen atom, and at the same time they both belong to the oxygen atom. The bonds created between nonmetals by atoms sharing electrons according to the octet rule are called covalent bonds. So electrons are not taken away from one atom by another atom to create a positive negative. They're simply shared. So covalent bonds share. An elemental diatomic molecule is a bond between 2 atoms of the same element in gas form only. Diatomic molecules are the most common covalent bonds in nature. There are 7 elemental diatomic molecules. 4 of these are halogens with 7 valence electrons. So they are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So one way to remember it is they form the number 7 over there on the right. From nitrogen, oxygen, fluorine, chlorine, bromine, iodine, those are 6, and then the 7th is hydrogen. So in nature, whenever you see these, they're never going to just be a hydrogen atom or a nitrogen atom or an oxygen atom. They're always going to pair up and form a molecule. That's 2 atoms put together. Notice those molecules are not compounds because they're the same element. Compounds have to be 2 different elements, 2 or more different elements. These are molecules, but they're not compounds. But these will occur frequently in the chemical reactions we deal with, that you'll have these paired up like this. So these elements always form diatomic molecules when they're in gas form. Polar covalent bonds happen when one of the nonmetals is slightly stronger than the other and pulls the electrons a little more towards itself. So if we look at, here we have 2 nonmetals. They're both strong guys. But fluorine has the highest electronegativity of any element on the periodic table. Nitrogen has a high electronegativity, but it's not as high as fluorine's. It's not as strong as fluorine. Therefore, fluorine is a little stronger. So what it does is it pulls those 2 electrons that they're sharing towards it. It doesn't totally take an electron away from nitrogen. It just tends to take nitrogen's electron as well as its own and pull it a little closer to the fluorine. So one of the atoms has higher electronegativity. It will pull all of the electrons closer to it, creating a polar covalent bond. What that means is the fluorine, because it'll pull the electrons towards it, will be more negatively charged. That end of the molecule will be more negatively charged. The nitrogen will have the electrons pulled away from it, so that end of the molecule will be more positively charged because the negative charges are pulled away from it. It's still an electrically neutral molecule. It still has the same number of protons as electrons. It's just the electrons are pulled over to one side, so that side of the molecule tends to be a bit more negative, and the other side that is having the electrons pulled away from it, that would be nitrogen, is a bit more positive. So fluorine is more electronegative, stronger than nitrogen, which is weaker, and pulls the electrons more toward it, but does not totally take them away. The atoms still share. The stronger atom in the polar covalent bond pulls a little harder than the other, but not hard enough to totally take the electron away from the weaker one. So oxygen is more electronegative than hydrogen, so it pulls the electrons toward it. The water molecule below is polar. So let's look at what's happening. Water is not a straight line or linear molecule. The hydrogens tend to be over on one side. And why that is, we'll talk about later when we get into the geometries of molecules. So what you'll notice, you can kind of artificially sector off this water molecule. You'll notice up in the red, all the electrons are pulled down towards the blue, down towards the oxygen. So up in the red, all you have are 2 protons. Those are the nuclei of the 2 hydrogen atoms, just a single proton. So the red area is a 2+ charge. It has 2 positive charges. If you go down to the blue, you have the nucleus of the oxygen. That has 8 protons. But what you'll notice is down in the blue is you have 10 electrons. You just count the electrons there. There's 10 electrons down there. So in the blue you have 10 electrons and only 8 protons. So the blue part is more negatively charged. So overall the molecule is electrically neutral. There's 10 electrons and 10 protons. But the electrons are pulled over towards the oxygen because it's a more polar, it's a more electronegative atom. So what you have down in the blue is more electrons than protons, so the blue area tends to be more negative. The red area has only protons in it, so it's more positive. So the hydrogen end of a water molecule, that's the red end, is going to be positively charged, and the blue side, the oxygen side of a water molecule, is going to be negatively charged. So this side of the molecule contains the nuclei of 2 hydrogen atoms, 2 protons. The red rectangle has a charge of 2+. This side of the molecule contains 8 protons and 10 electrons. The blue rectangle has a charge of 8 minus 10 or 2- charge. A polar molecule is an electrically neutral molecule. It doesn't have to be electrically neutral, but in this case we're going to emphasize that most are electrically neutral, that has a positive side and a negative side. This means that it acts like a magnet when other polar molecules are nearby. Covalent bonds form molecules. These water molecules, for example, are separate structures from all other water molecules. When water boils, the water molecules separate and move freely. So when you boil water, what you're seeing when you see steam coming up is water molecules that have broken away from the liquid that's down in the pan, and they now can fly off separately, independently from each other. So like that, the 2 water molecules can actually form independent structures that move apart. Think of molecules as cars that can move independently of one another. Ionic bonds form crystal lattice structures. Table salt, which is sodium chloride, has the formula NaCl. There is 1 sodium atom for each chlorine. So just to highlight one of the chlorines, the blue chlorine is attached to 4 sodium atoms. It's actually attached to 6, because remember, this is a 3-dimensional structure. We're showing it as 2-dimensional, but there would be a sodium on the side of the chlorine closest to you on outside of the screen, and back inside the screen on the side of the chlorine away from you. So there's actually 2 more sodiums, but we're just showing it as 2 dimensions, so we're going to say that there's 4. So that chlorine doesn't belong to any one of those Na sodium atoms. It belongs to all of them equally. NaCl is called a formula unit or unit cell because it identifies that there is 1 sodium for each chlorine. The formula unit is not a separate structure in the way a molecule is. Now sometimes when you see NaCl, it will loosely be referred to as a molecule. It really isn't. A molecule is actually, like we saw with water, a separate structure that can move independently of other water molecules. If you look at this structure, it's more like bricks in a wall, or I like to say like apartments in an apartment building. They're stuck together. So while there is one Na for every Cl, and so the formula unit is NaCl, they're not free to move about. One Na and one Cl are not free to move about the way a water molecule is. They're kind of stuck in that formation. So there's that Cl in blue that we were talking about. It's attached to those 4 Nas. So it doesn't belong to any one of the Nas. It belongs to all of them equally. A formula unit defines the smallest basic unit of a crystal lattice structure, but it is not a separate structure. By repeating a formula unit, the entire crystal structure can be created. So if you take a formula unit of NaCl and keep repeating it, then you end up with a crystal of salt. But you will never find a single NaCl by itself in isolation. A formula unit is like an apartment in an apartment building. An apartment can be distinguished from other apartments, but it is not a separate structure that can move independently like a car. Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. So we've learned this diagram of an atom. We show the protons and neutrons in the nucleus. In this case, of beryllium, it has 2 orbitals, so its first orbital is filled. It has 2 electrons, and then it has 2 more valence electrons that get separated there in the outside. So that's a standard diagram of an atom that we've had so far. But now you're going to see a simpler construct of an atom. Write the atomic symbol, so beryllium, it's Be, and then draw only the valence electrons around the symbol. So you ignore those core electrons. They're not important in chemical bonding. Only the valence electrons are. So for a Lewis structure, you're not going to draw the core electrons. You're just going to draw the valence electrons exactly the way that we've drawn them there. So that's why I had you draw the electrons the way I did. Place 1 at the bottom, 1 off to the side, 1 to the top, 1 to the right, and so on. You keep repeating. So there's a reason for that way of drawing. So this electron would go there, and then this one would go there. And that's the Lewis dot structure for beryllium. Lewis dot structures show only valence electrons since only these electrons are involved in chemical bonds. Let's look at an oxygen atom. So Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. So here's oxygen, so you draw the O. And then you go ahead and place those valence electrons the same way that you see them on that diagram of the atom. So the first one's going to go there, second one. So you can see they take up the same configuration they had on the diagram over there, but you neglect to draw the core electrons, the 2 inner orbital electrons. Let's do one more, phosphorus. So that's the diagram you would get of phosphorus. Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. So you're going to write the P, and then those 5 valence electrons are going to get moved over in the same location that they are in the diagram. You're just going to spread them around like that. Lewis dot structures are more than just a simple way of diagramming an atom. You can actually do some very powerful analysis of molecules, including the actual 3-dimensional geometric shape of a molecule by knowing its Lewis dot structure, by using Lewis dot structures. The Lewis dot representation of a water molecule is shown below. So there you see the oxygen, the way we drew it earlier. It doesn't matter which side you put the two, notice there's 2 pairs of electrons on oxygen, and there's 2 single electrons. It's the single electrons we're really interested in here because they're the ones that have an open space, an empty space, to take in the hydrogen. We saw that earlier. So all atoms want to fill their valence orbitals. Oxygen agrees to share one of its unpaired electrons with a hydrogen if hydrogen shares its electron with the oxygen. So we see that over there On the left, right there, they're sharing electrons. So now the hydrogen has a full valence orbital. Oxygen repeats this process with another hydrogen. So now it shares its electron with the other hydrogen, so the hydrogen has a full valence orbital, and now the oxygen also has a full valence orbital, 8 electrons in its valence orbital, in its outer orbital. Both hydrogen atoms and oxygen end up with filled valence orbitals, creating a covalent bond and fulfilling the octet rule. Covalent bonds form molecules. So water is a separate structure. Unlike NaCl, you can actually move one water molecule apart from another, and it can fly off into space if you boil water. That's not true of NaCl. An elemental diatomic molecule is a bond between two atoms of the same element. Elemental diatomic molecules are the most common covalent bonds in nature. There are 7 diatomic molecules. 4 of these are halogens with 7 valence electrons. So we've seen this earlier. So here's one of the 7 elemental diatomic molecules. You see that each fluorine has an empty space, so they can come together. And now they create octets for each other. So each of those fluorines now has an octet with those 2 shared electrons in between them. Okay, again, the electrons in between the fluorine are called bonding pair electrons. The ones that are on the outsides that aren't bonded to any other atom are called lone pair electrons. So each oxygen below has 6 valence electrons for a total of 12. So here's 2 standard oxygen atoms the way that we've drawn them before. How can we create 2 octets from 12 electrons? So in the valence orbital of each you have 6 and 6, that's 12, but you need an octet, which is 8. How do you form, that would seem to be 16 electrons to form 2 octets, but you only have 12 electrons to work with. So it's kind of like a little puzzle. How do you get 2 octets, an octet for each of those 2 oxygen atoms, when you only have 12 electrons in the valence orbital total to work with? And that's the answer. Each oxygen shares both of its unpaired electrons to form what is called a double bond. Notice that each oxygen atom has 8 electrons in its valence orbital because the electrons in the yellow area are counted for both atoms. So again, if you count the 4 in the yellow for the oxygen on the left, then you have those 4 plus the 2 lone pair that you see on the outside orbital over to the left. That's a total of 8. Then you count those 4 in yellow for the atom on the right. They get double counted. And then you have the 2 lone pairs way over on the right in the valence orbital for 4 more. That's a total of 8. So both of those oxygen atoms have octets. Double bonds are stronger than single bonds. They are also shorter than single bonds. That might seem a little counterintuitive. You have 4 electrons in there instead of just 2, but they actually pull tighter together. So it's a shorter bond length between them, and it's a stronger bond. The Lewis dot structure diagram for the O2 molecule looks like this. So there you see the double bond in between the oxygen. In a covalent bond, electrons that bond 2 atoms are called bonding electrons. So you have 2 pairs of bonding electrons in that double bond there. Electrons that do not bond 2 atoms are called non-bonding electrons or lone pair electrons. So get used to those terms, okay? You're going to hear those a lot. A pair of bonding electrons can be represented by a line. Lines should not be used to represent lone pair electrons. So you have the double bond. So each of those lines represents 2 electrons. So you have a double bond there with a total of 4 electrons in between the 2 oxygen. You should not use the lines for those outside electrons. Okay, it's just not done. In fact, usually when you use line representation, you don't even show the lone pairs on the outside. It would just be O, 2 lines, another O, and that's it. Okay, so let's try another one. Carbon dioxide, CO2, is what you exhale when you breathe. How does a carbon bond bond with two oxygen? There are a total of 16 valence electrons between the two oxygen and the one carbon atom. So if you draw the Lewis dot for oxygen, you end up with 6 valence electrons. With carbon, you end up with 4 valence electrons. So 6 plus 4 plus 6 is going to be 16. But you need to create 3 octets, one for the oxygen, one for the carbon, and one for the other oxygen. That's a total of 24. So how do you do that? So by creating double bonds between the carbon atom and each of the oxygen atoms, octets can be formed around each atom. Carbon forms double bonds with each oxygen. This provided octets for all 3 atoms. So just convince yourself that each of those atoms has its own octet, and you count the bonding electrons for both atoms that are being bonded to it. The Lewis dot structure of a carbon dioxide can be drawn with lines to represent a pair of bonding electrons. Carbon dioxide, CO2, has a balanced charge. The 2 oxygen atoms pull on the electrons equally, so the charge is equally distributed. So unlike a water molecule, which was kind of lopsided, the hydrogens were over on one side, carbon dioxide is balanced, it's symmetrical. So when electrons are not pulled to one side of the molecule is said to be nonpolar. So carbon dioxide is a nonpolar molecule. The oxygens are pulling equally in both directions, and so it doesn't have a positive side and a negative side. Generally speaking, when molecules are symmetrical, they look even like this, they look balanced, they're nonpolar. When they look lopsided, the way a water molecule does with the hydrogen over on one side of the oxygen, then they tend to be polar. In a metallic bond, electrons are attracted to the protons in the nucleus, but the electrons are not held closely to any particular atom, so they jump from one atom to the next when they are pushed. Copper, abbreviation Cu, has low ionization energy, so it easily passes electrons from one copper atom to another. The yellow copper circles, Cu circles, represent the nucleus of the copper atom and all the core electrons. So what you see flying around there are just valence electrons. The blue circles represent the copper valence electrons. So in other words, you have atoms of the same element. They all have equal electronegativities and equal ionization energies. So one is not any stronger than the other. But what you have is electrons that are way out in a higher orbital. For copper, they're way out there. They're quite a ways away from the nucleus, so they're easily separated from the nucleus of any one atom. So they tend to fly around like this in between atoms. So this would be like a piece of copper wire. The electrons are doing this in a piece of copper wire. This is called the electron sea model because electrons move around like fish in the sea. So they'll just kind of jump around. Now, if you put a negative pole at one end of those copper atoms and a positive pole at the other, it will push the electrons away from the negative pole and towards the positive pole. That will create a flow of electrons that we call electricity. But just a copper wire that's not attached to a positive and negative pole, the electrons are still flying around. They're just flying around kind of evenly back and forth like this. And that creates a bonding effect. We don't have to get any deeper into it than that. It does create a bonding effect. This constant changing of positives and negatives by those electrons flying around does cause the atoms to bond together very tightly, like a piece of metal. Okay, so here's a comparison of ionic and covalent bonds, and you should kind of become familiar with these. So an ionic compound creates a structure called a formula unit, and ultimately you put those together to get a crystal lattice structure. So again, think of a grain of salt. A lot of Na's and Cl's stuck together. They're not independent structures. Sometimes loosely they are called molecules, but that's not really a proper use of the word molecule. So NaCl can be referred to as the molecular formula for salt, but it's not a molecule. Covalent bonds actually form independent structures like that are called molecules. So think of water. Just think of H2O and how water can boil and the water molecules can separate from each other when you boil water. Bond formation. Ionic bonds, they pass electrons. One atom completely takes an electron away from another. That forms a positive atom called a cation and a negative atom called an anion, and the positive and negative attract each other. Another point is ionic bonds are formed by exactly two compounds, and they have to be charge balanced. When you put an ionic compound together, you have to have the same number of positive charges as negative charges sticking together, and there's exactly two compounds. With covalent bonds, they share electrons, and as you're going to see very shortly, covalent bonds can have multiple atoms in them. They can have many, many, many atoms in them. That's why your body, which requires very long, complex molecules, is formed with covalent bonds. Elements involved. So ionic bonds are metal and nonmetal. Weak guy is the metal, nonmetal is the strong guy. So it's a strong guy, weak guy relationship, and the strong guy takes the electron away from the weak guy. Covalent bonds are two nonmetals. Those are two strong guys. Neither one can win the tug of war, so they share electrons. Physical state. Ionic compounds are in solids. The moment you put salt, NaCl, into water, it dissolves, but it doesn't dissolve into NaCl molecules. It dissolves into Na plus ions and Cl minus ions. We're going to see that later on. Okay, so the ionic compounds are in solid form. They're generally not in liquid form except under extreme conditions. Covalent can be either solid, liquid, or gas. Melting point. Ionic compounds have a higher melting point. Covalent compounds have a lower melting point, or covalent molecules. Solubility in water, high. Just think of salt dissolving in water. Covalent bonds is low. And conductivity, that means of electricity. Ionic bonds, because in water they form cations like Na plus and anions like Cl minus. They're charged particles. They can easily conduct electrons, which is what we call electricity. Covalent bonds don't form positive, negative charges in water, and so they don't conduct electricity well. We'll see more examples of each of these principles at a later time in a lab. So that takes care of covalent bonds, all right? So we've covered all three types of bonds. We're really rarely going to talk about metallic bonds. There's not that much to talk about with them. But the two major types that we're going to talk about in this class are ionic and covalent bonds. Those are the last two lessons. So be sure you understand those well, how they're formed, and we'll go into more detail about covalent and ionic bonds in later lessons. Okay, that takes care of this lesson. We'll see you on the next lesson.